How's it going out there today? Welcome to my channel. We do educational material on this channel. We try to look at different theories of everything, and we go deep in depth and kind of just try to walk you through it. Things that are generally pretty esoteric, difficult to understand, and we just try to methodically go through it and sort it out. And today is our, I think, 393rd video that we have done on the reciprocal system of theory. It's possibly 394. But that theory was originally, the reciprocal system of theory was originally derived by Dewey B. Larson. Mr. Larson was an American engineer who lived in the 20th century, and he died in 1990, but not before he put out a lot of great books and articles and gave talks, and most of all of them were trying to forward his reciprocal system of theory. He first articulated that theory in 1959 publicly with his two fundamental postulates, and then he took his postulates through a process of deduction and if this then that, if this then that, and arrived at his theoretical universe after many steps. I go through that in a series of about 15 videos that I did about a year ago under the title of The Outline of the Deductive Development of the Reciprocal System. And when Larson arrived at his theoretical universe, he then compared his universe that he got strictly from theory with the scientists' own universe that they had observed and measured and compiled over the millennia, but particularly more recently in their scientific tables, their atomic tables, all of the different statistics that they had compiled about the various stars and galaxies and atoms and compounds and such like. And it's amazing to see how Mr. Larson was able to pull out these numbers, almost identical numbers, just from theory, especially when you consider that it took an army of scientists centuries or millennia and trillions of dollars to come up with the same tables. So you may ask, what is the general nature of Mr. Larson's theory and enabled him to do this? And again, that is primarily in his fundamental postulates, and primarily in the first fundamental postulate of two. His first fundamental postulate states that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. So, paraphrasing, the universe is not made out of matter, it's not made out of energy or force or anything else. It is made out of motion. And specifically, it is made out of something that he calls scalar motion, which is really like a non-localized motion or a pre-existing motion, an omnipresent motion, a motion that has a magnitude but has no specific direction. And the best way to or not the best, but maybe the best, but um, I guess one way to envision scalar motion is to take a balloon with dots on it and to blow up the balloon. And you observe that all of the dots are moving away from each other. Each dot is moving away from each other dot, but in no specific direction. Every location on the surface of that balloon is moving away from every other location. So you can't determine what direction they're moving in until you assign one arbitrarily as being motionless. When you do that, then you can start to figure out the directions. So the directions come from the reference point, not from the motion itself. So Larson uses this scalar motion, which has been recognized by scholars, or at least pointed to by scholars, because our telescopes have showed us that all of the galaxies, particularly the distant galaxies, are moving away from each other. So the galaxies apparently participate in a similar kind of motion. But the scientists have never investigated its properties. But Larson uses this scalar motion to build his universe of motion. And so the universe is not made out of matter, not made out of energy or anything else. It is made out of scalar motion. Just call it motion. And motion is the relationship between space and time. Hence the reciprocal system of theory, because space and time are reciprocals of one another. First, that means that they have the same qualities, but in inverse order or in inverted roles, and they do not exist in and of themselves. They only exist together in motion. So you can abstract space or you can abstract time, but you are really basically turning off or shutting off, abstracting. You are basically the same as if you assigned a reference point. You're stopping the universe, and that's enabling you to abstract space or time. But in reality, neither one of them exists by itself. They only exist together in motion. Motion is basically a fraction with time or space as the numerator and space or time as the denominator. But space or time can come in multiple dimensions. And Larson uses the three-dimensional idea of what he calls coordinate space, X, Y, Z coordinates. We generally observe space to have, volume, 3 dimensions, 3 orthogonal dimensions that are apart from 90 degree angles apart. And since space has this quality, time also has this quality, he presumed. And so he calls that coordinate time, 3 dimensions of time in a stationary frame. And then he uses the term clock space and clock time to refer to the scalar motion. Time is always getting later and later and later, but in no specific direction. Space is always getting farther and farther and farther apart, but in no specific direction, just like on the surface of a balloon. And then space and time both come only in discrete units. You have to have a minimum. Motion as well comes only in discrete units. If you have exactly 1 unit of space in 1 unit of time, you have what Larson, what everybody else calls the speed of light. The speed of light is what Larson calls unit speed. 1 over 1 equals 1. And And unit speed for Larson, just like any reciprocal of 1, is at the center of a reciprocal system. If you have, say, 3 1/3, 1 is at the center of those. That balances it out. If you multiply 3 by 1/3, you get 1. And so they are basically balanced out on the system of 1 in the center. And it's the same with all other, reciprocals. They multiply to get 1, which means that you have a balance there. Now, normally legacy scientists, they measure their quantities from 0. 0 is their reference point. Is it going, something from 0, +1, +2, +3, +4, +5, or -1, -2, -3, -4, -5 are the balances. With a reciprocal system, you have 1, and then you have 1, 2, 3, 4, 5, or 2, 3, 4, 5, and 1/2, 1/3, 1/4, 1/5. And so in Larson's system, 1 unit speed, or the speed of light, is the center, which means that it's also the 0 point, the null point, the neutral point, the really empty universe, or the nothingness of the universe. If you have absolutely nothing in the reciprocal system, you have motion outward at the speed of light, the origin. And that flies in the face of legacy science, which says that the speed of light is the maximum speed of the universe. Larson is saying that the speed of light is the midpoint of the universe, which means that half of the universe is actually moving faster than the speed of light, which he refers to as the cosmic sector, that legacy science knows nothing about. And then there's the more common and well-known material sector, which is the half of the universe that's moving slower than the speed of light. And these two sectors are reciprocals of one another. In the material sector, you have coordinate space, 3 dimensions of XYZ coordinates, still frame. And you have clock time. The clock is always getting later and later and later. In the cosmic sector, the sector moving faster than the speed of light, once you cross that speed of light boundary, then you have coordinate time, 3 dimensions of time in a still frame, and you have clock space. The clock is always getting further and further and further apart, but in no specific direction. So you can see that they have the same qualities, but with the roles of space and time reversed. So Larson starts from there, and then he derives his universe. Now, what we're looking at today is second installment of a paper that Larson gave called The Fundamentals of Science in the 21st Century. And he gave this talk back in 1978, so he was predicting the future, kind of. And we had already started this yesterday, so if you want to get to the start of the article, you want to listen to yesterday's episode. But today we're going to take over here toward the middle, and he went over in the first day kind of the history of science, going all the way back to the ancient Sumerians and the Egyptians and Babylonians and the ancient Greeks. He looked at the Ptolemaic theory, and then he went up to the scientific revolution of Copernicus and Galileo and Newton, and then eventually talked about the relativity theory and quantum mechanics in the early 20th century. And hopefully we can kind of take over here. I'm going to just back up one paragraph. The point of all this is that the invented, now he contrasts between invented theories and the inductive theories. The point of all this is that the invented theories of present-day science have exactly the same logical standing that the Ptolemaic theory of astronomy, the natural place theory of gravitation, and the other theories invented by the Greek scientists had in their day. They are mathematically correct, but conceptually wrong. This statement may seem to be in direct conflict with the many confident assertions in scientific literature in the effect that the fundamental theories of modern physics are established beyond the shadow of a doubt. That if one examines the basis for these assertions, one finds that the evidence that is cited is purely mathematical. What has been established is that the theories produce the common mathematical results. The correct mathematical results. Like all other inventive theories, they have been specifically designed to produce these correct results, but none of them is unique. In each case, there are alternatives that produce the same result. And as Richard Feynman points out, there is no scientific criterion by which we can choose between any two of these alternatives because, quote, they both agree with experiment to the same extent. So two theories, although they may have deeply different ideas behind them, may be mathematically identical, and then there is no scientific way to distinguish them. He goes on to say, quote, every theoretical physicist who is any good knows 6 or 7 theoretical representations of exactly the same physics. What Feynman does not say is that these comments apply only to invented theories. They have no relevance to theories derived by induction from factual premises. The kinetic theory of gases, for instance, is an inductive theory. It explains gas laws in terms of the motions of the molecules of which the gases are composed. No one knows a half dozen other representations of these gas laws that are equally correct, or even one such alternative, because it is tied in to experience, physically as well as mathematically. The kinetic theory is unique. It is both mathematically and conceptually correct. In inventive theories in general, including modern theories such as relativity and the quantum theories, are mathematically correct but conceptually wrong. This is not because of any errors in their construction, but by reason of their inherent nature. Whether there is any net gain in using inventive theories during times when the scientific community would otherwise have no theories at all to account for some of the important observed phenomena is an interesting philosophical issue. Inventive theories are not actually necessary. The mathematics, which always antedate the theories, could be used equally well without any theoretical explanation. So the issue boils down to the question, is a wrong explanation better than no explanation at all? There is a widespread tendency, dating back at least to Francis Bacon, to answer this question affirmatively. The argument being that a plausible explanation, even if wrong, will suggest some lines of further investigation that may be productive. On the other hand, it is easy to see that insistence on adhering to Aristotle's inventive theories was a serious impediment to scientific progress, particularly in the latter years of the ascendancy of Greek science. It can logically be deduced that insistence on adhering to the modern inventive theories is having a similar effect today. In any event, the fact that now needs to be recognized as we approach the 21st century is that we have once more arrived at the kind of a situation that developed in the Middle Ages. The currently accepted fundamental physical theories derived by pure invention have come to be overloaded with epicycles, while coincidentally, the development of inductively based theory has caught up with the empirical discoveries, so that the way is now open for a return to the firmly based inductive type of science. The imminence of another policy reversal could easily be deduced from nothing more than a consideration of the times involved in the cycle of reversals just described. The first inductive sciences prospered for thousands of years before they were overthrown by the Greek inventive science. The first inventive science then endured for about 2,500 years before the second of the inventive sciences, the one commonly associated with the name of Newton, took over. The accelerating pace of science is evident in that only about 400 years later, this vastly improved inductive science was replaced by the second inventive science, the one now in vogue. Almost 100 years more have elapsed. On the basis of a continuation of the same accelerating trend, it would be safe to predict, even without the benefit of additional information, that another reversal of policy is now due. The fundamental principles of 21st century science probably will be those of a third inductive science rather than the inventive concepts of 20th century physics. That argument is utterly unconvincing to me because it also means that soon thereafter you would have another cycle of inventive sciences coming right after that. And then right after that, you would have another cycle of inductive science, and so on, because the time cycle has shortened, and you're going backwards and forwards between the two. It just doesn't, is not convincing. It's about the most unconvincing thing from Larson that I have ever read, in my opinion. But we will continue on. But we do not have to depend entirely on inferences of this kind, as there is plenty of direct evidence leading in the same to the same conclusion. The epicycles already have multiplied to the point of absurdity. The history of quantum theories, for example, consists of a long series of modifications and conflicting interpretations which have made the theoretical structure practically unintelligible. Feynman, who should be in a position to assess the situation, tells us flatly, quote, "I think I can safely say that nobody understands quantum mechanics." End quote. The situation with respect to atomic structure is similar. The most popular pastime in physics today is inventing properties by which to characterize quarks, the elusive particles of which the constituents of the atom supposedly are constructed. No one has ever seen or otherwise observed a quark, or anything that could be a quark. Indeed, one of the most urgent objectives of the theorist is to produce a plausible theory that will justify asserting that quarks are inherently unobservable. Nevertheless, we are told just what kinds of quarks can exist and what their properties are. Properties with such interesting names as color and charm. In order to put this situation into the proper perspective, we should realize that while quarks have never been observed, the particles that are supposed to be constructed of quarks have never been observed either. Of course, these particles, the hypothetical constituents of atoms of matter, are called by familiar names, such as electron. But as we saw earlier, the properties that a particle must possess in order to play the part of the hypothetical electron in the atom are altogether different from those of the electron that is observed experimentally. There is actually no adequate justification for calling them by the same name. As Professor Herbert Dingle points out, we can deal with the electron as a constituent of the atom only if we ascribe to it properties not possessed by any imaginable objects at all, end quote. This question of atomic structure provides a good example of the difference between induction and invention. Such men as Newton and Einstein recognized the difference very clearly. Newton emphasized that he did not employ invention with his quote, hypotheses non fingo, I invent no hypotheses, while Einstein condemned Newton's inductive approach. But both procedures start in the same way, with a hypothesis. And this has confused the issue for many individuals. The difference lies in what happens when the hypothesis has been tested and found to be wrong. The Newtons then either discard the hypothesis or modify it drastically. The Einsteins invent something that eliminates the discrepancy so that they can retain the original hypothesis. When it was first discovered that atoms disintegrate under appropriate conditions and emit particles, in so doing, the hypothesis that the atom is constructed of such particles was very plausible. But as we have seen, when this hypothesis is put to a test, it fails, because the emitted particles are not capable of forming an atom. The inductive scientists, the Newtons, then have to abandon the hypothesis that an atom composed of particles and try to formulate some other hypothesis. But the inventive scientists, like the Einsteins, add some epicycles. They simply assume whatever it is necessary to make the particles fit the requirements, and they retain the original hypothesis. This is the situation that exists today. Present-day theorists are obsessed with the idea that they must continue to subdivide matter until they come to an elementary unit. So they invent atomic constituents. They invent forces such as the strong force to hold these invented constituents together. They invent quarks from which to construct the invented constituents. And there is even a suggestion that it may be necessary to invent a subquark, the so-called superstrings of infinitesimal length and zero width. The particles of physics are rapidly approaching the status of the fleas in the popular little verse, "Big fleas have little fleas upon their backs to bite 'em. The little fleas still smaller fleas, and so on ad infinitum." When we reach the point where further subdivision cannot be accomplished without invention, as is now the case with the atom, this tells us that the atom is not composed of smaller units of matter, but is composed of some other more fundamental entity. We will take up the question as to the entity of this as to the identity of this entity shortly. In the meantime, let us return to the question of inventive versus inductive science. While the position of the prevailing inventive science has been deteriorating, a large number of individual advances in different physical fields have extended a solid framework of inductive theory far beyond the level at which it stood in the early 20th century. Scientific knowledge at that time was too limited to provide the necessary foundation for an inductive theory of the far-out regions into which observation was beginning to penetrate. This was the reason, of course, why inventive science gained the ascendancy. A few of the essential building blocks were already in place. The discrete nature of the units of radiant energy had been demonstrated, radioactivity had been discovered, electric current had been identified as a movement of electrons, and so on. But an immense amount of additional information had to be accumulated. That information is now available, and the final addition to the inductive structure needed to make sorry about that. Let me just turn that off here. I think I'll try to get rid of that clock here because I don't know how to turn the alarm off with it. Okay. A few of the essential building blocks were already in place. The discrete nature of the units of radiant energy had been demonstrated. Radioactivity, okay. That information is now available, and the final addition of the inductive structure needed to make it capable of dealing with the entire body of current empirical knowledge as it now stands, has been provided by a new theoretical development. This development is the subject of my published works and those of my associates. Its basic outlines will be presented in the next 3 chapters. Don't know about what chapters he's referring to, but we are going to finish with that and move on to the next section tomorrow. So thanks for tuning in today, and come back tomorrow.